Okay, 6 o'clock. It's our last week of content before the next exam, so that went by quick, didn't it? I think it has. So tonight we're going to take a look at the definite integral. The last problem we'll take a look at is what we were looking at earlier on when we were doing Riemann sums, and we'll look at an easier way sort of to get it, the exact value, without having to do an infinite number of rectangles. And it will tie together what we started in 13.1. Okay, so we're kind of going back to the beginning, using the same techniques. So there's really not a new technique as far as doing integration, but just a little addition to it, and will keep us moving forward. On Thursday, we'll take a look at the area between two curves, because what we do tonight will actually be the area under a curve and the x-axis. So to get the area between two curves, all you got to do is subtract the two. So it'll actually, once we get tonight's content, it will be pretty much what we're doing. The other one is graphically, you look at two curves and you just subtract, you'll get the distance between them. Okay, so it's really nothing too much newer. We'll have, now if you go to the MAT210 website, ASU's website that's in the syllabus, I've got, it's always been there. They have the practice test already. I'll make sure it's also all uploaded into Canvas, along with any review videos and such that I have, so that by, so this Thursday we covered the last content. Over the weekend, it'd be good if you could get as much of the review as possible, and then we can talk about it. Yes?
Is there any way you could do an exam review session like how you did for the last test? Like not right before, because I have two classes before the test. Last time I had to ditch both of those to go to the review. Is there any way we could do it like before, or like, I don't know if there's another solution. Because if not, I can just ditch again, but it's not really the ideal.
Let's take a look. So that's next week. Oh, next week's going to be...
If not, it's totally fine.
Tuesday. Oh, I'm in the wrong. Probably. We could probably make something work out. Have to look at my schedule. We might, it would probably have to be like a Wednesday afternoon. We, yeah. And again, if we could, if over the weekend, maybe if you could get into some of the reviews, and I think we might be able to do it because it's going to be shorter as far as the amount of stuff we have. So let's see how much we can get covered on the review day. We'll actually, instead of just showing what's there, we'll actually go ahead and start working through some of the review questions. And then we could look at what maybe is needed for that Wednesday.
Thank you, I appreciate it.
Sure. Okay. And I am not sure. Got some videos. Let's see if I have. Yeah, I might not have anything on the review. We'll take a look to see what I can get out there. But let's kind of move forward today. And maybe we can even throw in a few on Thursday. Okay. So, again, nothing really earth-shatteringly new tonight, but we're going to connect the definite integral with indefinite integrals. Okay, so the indefinite integral is what we started with, just finding the antiderivative, right? We just found it, and then we had always had this plus c. What we're going to find out tonight is when we do what we call the definite integral, which is a an interval, just an interval under the curve, that constant would cancel out, so we don't actually really need it. So we're going to start with, what happened here? I thought maybe I didn't get it saved. Well, let's go ahead and see where we go from here. Okay, so here's an example. We're in integration, so what we always start off with is a derivative function. So notice we're given the marginal cost, which is a derivative, marginal cost function, dollars per cap, so that word per is indicating it's a rate. It's a rate function. So this is a derivative that we've been given, and then we're asked to find the total charge of cost if the production is increased from 100 to 200. So we've got a formula that is a rate, right? It's a derivative, but we want to get the actual cost, which is a value. It's not a rate. So what do we need to do? We need to integrate. We need to find the antiderivative. We need to find where did this function come from? What was this function before they took the derivative? Okay, so since what we're given, the marginal cost, is a derivative, we will find the indefinite integral by integrating the function 4 minus 0.001x. And if you remember, this is like 4 is like x to the 0. So remember, when we integrate, we add 1 to the exponent, and then we divide by that exponent. So the first term becomes 4 x to the first power divided by 1 if you want, which is just 4x, right? Okay. The second part, we have x with a 0.001, so there's a negative 0.001. We add 1 to the exponent, which the exponent is 1. 1 plus 1 is 2, and we divide by that new exponent. Okay, and then we have plus a constant. Okay, so that's what we started off with way back in 13.1, right? That's all we're doing. But what we're going to do is we're going to take, because the question is specifically what happens to the cost going from 100 to 200 caps, we have a boundary. So what we're going to see is those will be boundaries that we put on the integration. Since we have this function, what would we do to find the difference between producing 100 caps and 200 caps? Wouldn't we just take the function that we found, the antiderivative, at 200 minus the cost at 100? Because we now have a cost function, don't we? It's not a marginal cost. It's a cost function that's going to return values, the actual cost. So we find out how much it costs to make 200 caps, find out how much it costs to make 100, and we subtract them. That's the difference, isn't it? And that's what this is asking us, is the change or the difference between making 100 and 200. Okay. And that's all these questions will have something. It's a difference between this many and this many. If they just wanted 200, we'd plug in 200, we'd be done. Sort of, because we don't know the actual function because of this, but watch what happens in the next slide. Okay, so they integrated 4x minus 0.001 x squared over 2 like we did, plus some sort of constant. We don't know what that is. They simplified a little bit. They took 0.001 divided by 2 and got 0.0005 plus this constant. Notice when we plug in 100 caps that they're going to make, we get the cost plus some constant. So it's, if you plug in 4 times 100, you get 400, you minus this, you end up with 395. So for 100. We do the same thing for 200 caps, right? We plug that in and we get that to make 200 caps, it's 780 plus a constant. And then when you subtract those two, what happens to the constant? We've got a positive constant here. We're going to subtract this, so that distributes to this term and this term. What is positive k minus k? It's nothing. It's 0. It cancels out. So we don't care what the constant was. We don't need to find it because it's going to cancel out in all of these situations. So this slide is just to let you know that we didn't just forget about the constant. It's that putting the constant's not needed because it will cancel out. Okay? And so we end up doing is 780 minus 395, and we end up with 385. That's the difference in the cost going from 100 to 200 hats, caps, or whatever they are, baseball caps probably. Okay? And what we just did is we did what's called a definite integral. We started with the integral. We're going from 100 caps to 200 caps, so there'll always be this boundary. Inside here is the function that is a derivative. And this is what we call a definite integral because it's got boundaries. When we don't have those, that was indefinite, means there's no boundaries on it, so we need that constant. And what we're going to see is all we need to do is find the antiderivative. Which we did. And then we're going to evaluate it between 100 and 200, which means we plug in the 200, and then we plug in the 100, and we subtract those two values. And that's what we're doing. And what we're going to get is we're going to get the area under this curve. So remember, this was a derivative curve. It was the marginal cost. But remember, when we were doing Riemann sums, we would do this derivative curve, and we would find the rectangles underneath it from a particular place. We were basically trying to estimate the area under the curve. What we're doing with this method is actually, even though we use the integrated amount, the value here, 385, it's the area under the derivative curve. So that's kind of, don't worry too much about it, but that's what we're getting. Okay. So let's go forward a little bit more. So we found the antiderivative, right? This is the x squared, there's that. We could have used any of the functions, which included the antiderivative, say plus 0 or plus 4, because when we subtract them, whatever that constant is or was, it would cancel out. Okay? So from now on, when we start doing here, this is my favorite part because I'd always forget this anyway, we don't have to worry about the constant. We just get the antiderivative, and we take the two boundaries, the upper boundary, and subtract it, plug it in, and subtract it from the lower boundary plugged into the antiderivative. Okay. Method 2 would simply be saying that, okay, we've got this derivative. Total cost would be the change over this interval. It would also be sort of what we think of as accumulation. It's the area under the marginal cost function curve. Okay, so this is what we were doing last Thursday with the Riemann sums. And so we could geometrically calculate it. So this here is the marginal cost, right? It's a graph of this function, and this is the area under the curve, and it's almost a rectangle anyway, so it's 100 times its height. It ends up being 385. Now we did that with Riemann sums, rectangles, right? So all this is saying that both of them work. What we're going to be using in this section is primarily we're going to get the antiderivative, plug in the two limits, the upper limit and the lower limit, subtract the two, and we're going to get our answer. We're going to get it exactly. We don't need to make 4 or 5 different Riemann boxes or 50 or whatever, because those are all approximations. We're going to get the exact value with this method that sort of brings everything together that we've been doing. Questions? Does it make sense? Did I lose anybody? Sure? Okay, good. So this is basically what we're going to do. Is we start off with every problem we have a derivative. It's a marginal something, it's a rate. We're going to integrate it or get the antiderivative, mostly by adding 1 to the exponent and dividing by that. We'll get some that might be natural logs and some that are exponentials, so those are the other ways, but primarily we deal with polynomials, okay? And then it's simply, once we get the antiderivative, we take the two boundaries, the upper limit and the lower limit, plug them in and subtract them, and we're done. So we'll do a few. So this has got a big name called the fundamental theorem of calculus. It's almost like then you hear bells or something. It's a pretty big deal. And it took people like probably hundreds of years to come up with this. They did Riemann sums for a long time, and then they figured out that they could do these. So everything we're going to do is, again, remember, this function here is a derivative. We're going from two limits, a to b, and once we integrate it, get its antiderivative, we plug those in, subtract them, and we'll have the values we need. So this is a little bit more formalized, but again, we'll work a few examples and you'll just get used to it. We find its antiderivative, and then we plug in the b, we plug in the a, and subtract them. Okay, so more words to it. So here's an example. If I need to integrate 2x dx, remember 2x is, because it's inside an integral, it's a derivative. That's what they're telling us. So we get the antiderivative, right? The antiderivative of 2x, you'd put a 2 up here, because you got 1 plus 1 is 2. Divide by 2, that cancels. So your function, your integrated function, is x squared. You plug the two limits, so f of 1, which is going to be 1 squared. You plug in the bottom function, the bottom limit, f of 0, which is going to be 0 squared. You subtract the 2, and what you get is that the area under the curve 2x going from 0 to 1 is 1. And again, you could visualize it here. What does 2x look like? Well, 2x is it's a linear equation with a slope of 2. So when x is 1, y is 2. And so that's the function. The area under this forms a triangle, right? It's got a base of 1, a height of 2. How do we find the area of a triangle? Part of it. Since it's a triangle, divided by 2, right? Because that would be if it was a rectangle, base times height. Triangle is 1/2 base times height. And what do we have? We have a base of 1, a height of 2, divided by 2 gives us a total area of 1. Okay, so we could do this geometrically like we've been doing, but we can also use this fundamental theorem of calculus and just get the antiderivative, plug in the two limits, and we'll get the same value. What we're getting, again, is the area underneath the derivative curve. Okay, it's not the area under x squared. We use x squared to figure that out. And remember, when we got the slope of the tangent line, what did we use? We used the derivative function, which gives us a slope of the tangent line to the original curve. So there's this thing going on in calculus where we have two curves. One is a value curve and one is a derivative curve, a rate curve. And we've been going, first part of the class, we've been going from the value curve to the derivative curve, the rate curve. Now we're going backwards. We're starting with the derivative curve, or the rate. We're going back to the value curve. Okay? So that's one of the things. So let's take a look at this one. Integrate from 0 to 1 this function. How would I integrate? And remember, we can do it term by term, so how do I integrate 1? So this is like x to the 0. I add 1 and divide by 1. So that's going to give us 1x to the first power over 1, or just x, right? When you've got a constant, it integrates just basically to x. How about what happens to x squared? Add 1 to the exponent, so x to the third, divided by the new exponent. So that's the key part. Yeah, so tempting to divide it by the old exponent, but 3, exactly. So we want to divide it by 3. It's got a negative in front, so that just kind of comes along. There we are. Plus a constant, but we're not going to mess with constants anymore because it would just cancel out, so let's not worry about it. And then what we like to do is over here we say, okay, we're going to take this new function, we're going to go from 0 to 1. So that's just kind of the notation to say, okay, we got our antiderivative, let's take it from 0 to 1. And what we do is we plug in 1 first, and then we subtract what happens when we plug in 2. So we're going to get x minus x to the third. We'll plug in 1, so that gives us 1 minus 1 cubed over 3. I'm going to put that into parentheses, just that's the first part of the function. And then from that we're going to subtract the same function when we put in 0. And I just love using 0 because a lot of times, like in this case, it ends up giving us 0. So there's that calculation's very easy, right? 0 minus 0 is still 0. Okay, so this whole part here is 0. So we end up with 1. 1 to the third is still 1. 1 minus 1/3. This part is, I guess you could put minus 0. So in the end, what's 1 minus 1/3? Well, 1 is 3/3 minus 1/3. We end up with 2/3. Okay. If you were to graph the original function, 1 minus x squared, which is let's see, 1 minus x squared, it'll be some kind of parabola. And then if you went from 0 to 1, you would find that the area was 2/3, or 0.667, right? 6666 repeating, 2/3. Does that make sense? Okay. So very technical, but that's all we're doing. So here's the written part, if you'd like. Again, it's just what we just did. They got the function x minus x to the third over 3, right? That's what we came up with. And then they're going to plug in, I guess that's how they did it. They did plus a constant, but since we're going to have a limit, right, we're going to find the function value at 1 and the function value at 0, which we did already. We don't really need that constant. We just plug it in, and that's what we got. Okay? And then they end up with 2/3. So everything we just went through, it's there in their writing as well. Okay, so I try to do that. We'll work through the solution, and there we go. Questions? Is that making sense? Does it feel comfortable? Okay, good. Because that's all there is to this stuff, really. We'll look at, and then now we're into applications. The only thing with the applications, there's words to it, but what we need to pick out of these words, skip over most of it, we need to find the function, and watch, I'll bet you somewhere it tells us that this is a derivative. One way they tell us is that it's thousands of barrels per day, so that's a rate, right? Your deep ocean oil rig has suffered a catastrophic failure. We've talked about this before. The oil is leaking from the ocean floor wellhead at a rate, so that's telling us this is the function they're giving us is a derivative, right? So if we're starting with a derivative, what are we going to try to get? Most likely an antiderivative. They tell us it's going from, t goes from 0 to 20, where t is time in days, and then they compute the total volume of oil released during the first 20 days. Now again, we did this in an earlier lecture. I can't remember which one, but maybe we just found the antiderivative. But what they're asking us to do now is to find this derivative, to find the integral, from 0 to 20, right, from the start to the end, which is 20 days, the first 20 days. This is the derivative function. And we could put a dt here. Notation's not real important, but that just tells us we've got a derivative in terms of t. We're going to find the antiderivative in terms of t, and then we're going to use the boundaries to figure out how much happened. And it will give us physically the area under the curve of this function. If we were to graph this and find its area, that's what we would get. That's what we're getting. Okay, so first let's integrate. What's 0.08 t squared? If we integrate it, it's going to become t to what power? The third, because we're adding 1. So that means we must need to divide by 3. And that 0.08 just tags along for the ride. Yeah, it's a constant multiplier. That's cool. What does 4t become? It's 4t to the 1 power. 4t to the 2 power, because we add 1 to it. And divide by the new exponent 2. So you might want to say 4 divided by 2 is 2, but I like to put every step in there just so you see what's happening. But we could simplify. And then this one sometimes is a harder one, but I've got a constant. When I integrate a constant, what do I get? What's that? 60x, or in this case t, but yeah, 60 times the variable. Good. So and then again, we've been putting plus a constant, but what I like to do is, it's to remind myself I don't need to, I put the line, I say, okay, because I'm going over an interval from 0 to 20, I don't need to put plus a constant, because that would subtract out anyway, right? It's not important. And then what do? I plug in 20 for t, so 0.08, 20 to the third, over 3. And this is why I don't spend too much time reducing it, because we're just going to do a calculation anyway. I'll just go ahead and do 4 times 20 squared over 2. Plug it all in my calculator, let it handle it. Plus 60 times 20. And then I'm going to subtract this whole thing, and I suggest always putting this parentheses, because if you've got numbers in there, that negative would have to distribute to all the parts. But again, when we're starting from 0, it's really nice, right? We plug it in, but can you see that we're going to just end up with 0? Because everywhere you put a t is going to go as 0. I'll go ahead and put that in, times 0 cubed over 3 minus. And the reason I'll do this is because I want to remind you, if it wasn't 0, that's what we're doing. If I just put 0, you say, okay, what happened back there? When I've got 0, I just plug it in just like everything else. Times 0. And all of these, because they all have a 0 in it, end up being 0 minus 0 plus 0. So it's all 0. Okay. So all we got to do is calculate this part, plug it in the calculator, right? We're going to get some bigger numbers. 20 to the third power is probably pretty big. 8,000 maybe. Maybe not huge, but. And then we multiply by 0.8 and all that kind of stuff. I think I got a calculator with me. And again, when you're doing these, just watch your order of operations as you put things into your calculator. Because if you don't get it in just right, you'll have problems. So 0.08 times 20 raised to the third divided by 3. Oops, that was a mess. 0.08 times 20 raised to the third, and then the whole thing, because when I divided by 2 it was up in the exponent. So I get, for this one, 213.3333 repeating. For this part we're going to get 4 times 20 to the second, 4 times 20 raised to the second power divided by 2. I end up with minus 800. Am I matching anyone else? Anyone else checking me on this? Because I'm probably the biggest mistake maker in the whole class, so when it comes to arithmetic. And then 60 times 20, I think I can almost do that in my head. That's 1,200, because of 2 zeros, right? 12 with 2 zeros on it. And now we add those 3 together. So we got our 213.33333 minus 800 plus 1,200 minus 0 if you want, right? This whole thing was 0. And I come up with 613.33333. Good? Okay, that's all there is to it now. We didn't need to make all these. That's why I said when we were doing the Riemann sums, don't worry too much. This is how we're going to get to it. It was just building us up that is how we get the area under the curve. We could approximate it. Now we can actually get it exactly.
I thought you would need to use like a 1/2 or 1/3 because you're trying to find the volume.
Not the volume. We're finding the area under the curve, but we're finding the area under the derivative curve, which has an x squared. So what happens is this will graph into something. It's a parabola. I don't know what it'll look like. I think it looks something like that. And so we're going from 0 to 20. And so what we're finding is, and again, this is the curve of the derivative, and what we're getting is the area under this curve. And it ends up being that if we find the antiderivative, we plug in the upper limit and the lower limit and subtract them, it gives us the area under that curve. There is also, see, this calculator will do it. Let me show you 0.08 x squared minus 4x plus 60. Oops. Squared minus 4x plus 60. And let's see, I'm going to just set up my window to go from 0 to 25. We'll go from 0 to 500. Okay. So let me, and again, we apologize to those watching the video. I'm going to show you how to use the graphing calculator. If I don't destroy everything in the process. So that was the derivative function. I haven't integrated, I'm using the derivative function, so that's what I would graph. I did set the window, I hopefully big enough, because I know I'm going from 0 to 20, so I went 0 to 25 just to go a little bit bigger. I'm guessing my y values probably go from 0 to 500. I might be a little bit off, but we'll see. I'm going to graph it. Actually, I didn't have to go to 500. That's what that looks like. And so what's happening actually is as it gets further, the leak is somehow getting sealed up, right? Because I have less leakage. But watch what happens. Let me go back to the window. Let's make it, maybe I'll only have to go to 100. And so we can see more of this graph. There is a function on the TI-84. I think the Casio still has it too, but I'll have to look that up. So we go second calc, and notice we've got number 7, which is the integration of the function. I'm going to hit that, and it asks for the lower limit. We were going from where? 0, upper limit of 20. Plug those in, and look what it does. It's telling us we're getting the area under the curve from 0 to 20, and man, we came up pretty good, 613.333. Great way to check it. So if you've got a TI calculator, you'll be able to check all your answers with this. Just remember, you're graphing the derivative function. We're getting the area under that derivative function. We do it analytically by getting the antiderivative, plugging in the limits, and we got it, right? We just did this, 613. Or we could see it graphically, graphing the derivative function, and we're getting the area under that curve. So it's a nice little feature that it has. Basically, this is what we were doing with, yes?
What did you type into the calculator to get the...
So I typed in, so this is the derivative function. Yeah, so it's what they gave us. So I didn't, it's cool, I didn't have to do hardly any math, right? I just plugged in what they gave me. I had to figure out the size of the window I needed to see, but they kind of give us some limit, you know, at least the X way, I knew I was going from 0 to 20, so that was easy to fit, and then I just had to play to make sure that my Y was big enough, but maybe not too big, so that I could see it pretty good. So then when I graph it, I'm there, and then I just use the built-in feature, the calc feature, so it's a second calc, it's number 7. It will actually integrate it for us, numerically integrate it. And then I put in my limits and draws the picture, and then I see what I'm getting. So it's a nice way to check. You'll be able to do this with all the questions you've got in the homework. Maybe sometimes you'll do it first and then move on, but it's good to also do it both ways. Make sense? Okay. And again, I apologize. My the one I have in my computer, somehow the ROM dropped out and I haven't been able to reinstall it correctly, so it's just what we are working with. And that's basically all we got tonight. The cool part is for tomorrow's class, Thursday's class, we're doing the same thing, but we're getting the area between two curves. So basically, we find both of them and just subtract them. Okay, we're not quite done, but all of the rest of this is just walking through you through the steps I've already gone through. So I'll just kind of, yeah, they did this. Got the same answer we did, but if you want to see it sort of written out that way. Now there's no more to go. Okay, the homework, there's like, I don't know, 7 or 8 where they just give you a setup of the, say, find the integration and then do the limits. There's a couple of applied ones. All it is reading through. They'll still give you the function as a derivative. You just have to set it up, but they'll give you the limits. Same thing. And again, you could use the calculator tool. Desmos has a similar feature in it, so if you want to use the online Desmos, look it up. Maybe look up the video. It's been a while since I've done it. I don't know if it will do it graphically, but it will figure it out for you as well. So there's various apps out there, but if you got a TI-84 or 83, it's a built-in function that will actually draw it for you and check it. And you see, we're done like half an hour early. I think Thursday will be done just as early, so maybe we could take on Thursday, I'll throw a few practice test questions at you. We'll get set up, so then over the weekend, maybe you could start working on it. When we come back on Tuesday, we could do more in-class review, just work through problems, answer questions. If needed, we'll set up a time Wednesday before the test, because that's all coming up next week, right? That took me by surprise. Wednesday, we'll set up a convenient time for as many as we can. We'll have a study session. We've also got our SI, right? So probably have a study session sometime. And then we'll have our test next Thursday. And do really well, that's the goal. Everyone who's here, I want to see you 90% or above. That's the goal. And then all we got is a few more sections. We go take our final, and remember the final, how you do on the final can upgrade test 1 or test 2. And get you that score that's going to make everything perfect for you. You don't want to take this class again, do you? All right. That's all I got. But if you got questions, hang around. We'll work some problems if you want. Thank you.
There is a slight issue.
Oh,
So this calculator. So look, the graphs are weird right now. So I'm like, okay, I'm just gonna. It wouldn't like a graph weird. So I'm like, let me just do y equals 1. Graph. Where the hell is it?
do a zoom standard. Zoom 6. 6 still doesn't have it.
Can you just go through my sig real quick? 'Cause there's probably something.
Yeah. Okay, here it is. Format.
Grid off. We need grid line.
There you. Okay. Yeah. And I think you're fine. No, that's. But it's not showing the axes either. So let's format. Label off. Axes off. Everything's turned on.
How did that?
Let's.
You're hilarious, bro.
Gray. Gray.
And then go grid off maybe again.
Yeah, maybe not. It doesn't have the axis. But the other way, if you don't have.
Ooh, I like this because that gives me those little lines.
Okay,
That's
there you
nice.
go. Yeah,
Perfect. Wait, how did? Oh, you go second.
I wasn't here on Thursday.
Oh.
Are you still able to download the
Yeah.
units?
Yeah. You heard about it though, huh?
Yeah.
Yeah.
This one.
Me as well.
You got it. You got it.
Yeah,
that's one
tell
of my
me to do
favorite
that real quick.
programs.
So they can program a real
Sure is.
Yeah.
Okay, so you are going to link, you're going to receive.
Well, you don't have your calculator. There's nothing you can do for you.
Oops.
You can't program it.
Link.
How many calculator,
I'm
bro?
going to send you a
How
program.
many calculator, bro?
Riemann
Just different.
transmit. It's there.
Thank you. See you, bro.
Strategy.
Let's see. Enter. Quit. Program.
Awesome, thank you.
Thank you so much.
My pleasure. Receive. Link. Send a program. Program. Done.
Hey, thank you.
Let's just make sure that program is in there.
Thank you.
You're welcome.
Have a great night.
You too.
I wasn't here last weekend to pick up my test. Did
Okay.
you already get rid of them, or?
Well, they're in my office.
Okay, I just come to your office hour.
Yeah, come on office hour, or send me an email and I'll bring it to class. But if you can come to office hour, then just get it there.
Okay, thanks, sir.
Thank you.
Where did you get the 640 over 3 from? Because I remember that. I got 213,
Let's
which
see.
I thought is what you got.
Yeah. So I got 213.33, but then this gave us 800,
Okay.
and then this gave us 1200.
Oh, then I just added this all wrong. So I didn't put it.
Oh.
That's what it is, right?
Well, actually, I got it after you divided by 3 this week. That's what this became. So if you take 108, well, I matched the book, so yeah, it should be 213, not divided by 3, because it's if you divide it by the first. So 0.08, 20 to the third divided by 3 should give you 213.3.
Got it. Okay, I think I added it all. Actually.
Okay.
'Cause that's-
Yeah, and
that-
then
yeah,
this
that-
is a subtraction. Yeah.
Okay. And then to get the
Graph. So you go there, and perfect. You've got the original function there.
Okay.
Oh, wait. The original function is just t squared and
Oh,
x. So
okay.
yeah, so do the original function.
Okay.
And then graph it. You might have to change. Yeah, we'll probably need to change the window because we're going to so go to window. You're going to want the x to go from say 0 to 25.
Alright.
And then the y's, I went from 0 to 100, just so I could see high enough.
Okay.
Again, actually I went 500, but that was too much. But you just play with it, and then now hit the
Okay.
graph. So we can see the graph,
Okay.
and then it's second calc. We're going to do number 7. Go down. It asks you for the lower limit, which we know is 0.
Okay.
So we just put 0, enter. It asks for the upper limit, that's 20.
And then just
20, yeah. So x equals 20.
okay.
Enter. And it's showing us what we're getting is the area under the curve, and that is 613,
That which is what that should be. Okay.
Yes.
Cool. Thank you.
You're welcome. Hey,
I need that software.
you got it.